Everybody wonders about Pluto. I mean, it's this extraordinary world. There's regions, there's dark terrain, light terrain, there's nitrogen snow.
What if Pluto, the icy dwarf planet at the edge of our solar system, holds a secret so shocking it could change our understanding of alien life forever? For decades, Pluto was dismissed as a frozen rock, a desolate outpost on the fringes of our solar system. But recent revelations have shattered that perception. Declassified data, including stunning images from the James Webb Space Telescope, suggests that beneath Pluto's icy exterior lies a mystery so profound it has scientists questioning everything. Is it possible that a hidden ocean, brimming with the potential for life, exists in this far-off world? Today we dive into the enigma of Pluto's frozen heart and uncover the secrets lurking beneath its icy shell. Pluto's heart-shaped glacier, Sputnik Planitia, has always been a defining feature of the dwarf planet. Stretching over 1 million square miles, this vast nitrogen ice field is more than just a picturesque landmark. It may sit atop a hidden subsurface ocean. Researchers believe that beneath this frozen expanse lies a reservoir of liquid water, protected from freezing by heat generated by radioactive decay in Pluto's core. The glacier itself is dynamic and alive, exhibiting strange polygonal patterns that scientists attribute to convection. This process, where heat causes ice to move and churn like a giant lava lamp, indicates that Pluto is far more active than we ever imagined. Adding to the mystery, the weight of Sputnik Planitia's ice appears to have shifted Pluto's orientation, creating a gravitational alignment with its largest moon, Charon. Beyond Sputnik Planitia, Pluto's rugged surface reveals towering mountains of water ice, some reaching heights of 4 miles, comparable to the tallest peaks on Earth. Cracks and faults crisscross the terrain, hinting at a dynamic crust flexing over a hidden ocean. These features have ignited discussions about the potential for life. Physicist Brian Cox posits that where there's liquid water, there might be life, even in its simplest microbial form. Yet the evidence remains circumstantial. NASA's New Horizons mission provided a tantalizing glimpse of Pluto, capturing detailed images of only 40% of its surface. The rest remains cloaked in mystery, awaiting future missions like the proposed Pluto orbiter. Such a mission could spend years studying the dwarf planet, confirming the existence of an ocean and exploring its implications for life beyond Earth. The discovery of a potential ocean on Pluto challenges the traditional boundaries of the habitable zone, the region around a star where conditions are thought to support life. If an ocean can exist here, in one of the coldest and most distant places in the solar system, where else might we find water and life? This revelation has scientists turning their attention to other icy worlds, such as Europa and Enceladus, which also harbor hidden oceans. Adding another layer of intrigue is Pluto's formation. Recent studies suggest it may have had a violent, hot start, with massive collisions generating enough heat to create a liquid ocean billions of years ago. This theory upends traditional views of how icy worlds form and evolve, suggesting that Pluto's ocean may have existed long enough for life to potentially emerge. Despite the numerous challenges involved in exploring Pluto and its mysterious Kuiper Belt neighbors, the scientific community remains deeply captivated by the potential discoveries awaiting in this distant frontier of our solar system. These icy, enigmatic worlds, lying billions of miles from the warmth of the sun, are not just remote and difficult to reach, they also represent one of the last great unknowns in planetary science. Reaching Pluto and its neighbors demands monumental investments of time, resources, and technology. Space missions to this region must contend with extreme distances, hostile environmental conditions, and limited opportunities for launch and exploration. Yet despite these hurdles, scientists are undeterred, driven by the belief that the potential rewards far outweigh the difficulties. The allure of uncovering deeper truths about our solar system, and perhaps even the origins of life itself, fuels their determination. One of the primary challenges is the sheer distance to Pluto and the Kuiper Belt. Even with the fastest spacecraft, it takes years, if not decades, to reach these outer reaches. For instance, NASA's New Horizons spacecraft, launched in 2006, took nearly a decade to fly by Pluto in 2015. This immense travel time requires spacecraft to be equipped with long-lasting power systems, such as radioisotope thermoelectric generators, RTGs, to operate in the frigid and dim conditions of deep space. Furthermore, once the spacecraft arrives, the window for collecting data is often brief. For New Horizons, the historic flyby of Pluto lasted only a matter of hours, underscoring the importance of precision and preparation in mission planning. In addition to the logistical difficulties, the Kuiper Belt's extreme environment poses unique challenges. The frigid temperatures, lack of sunlight, and sparse availability of data from Earth make it difficult to design instruments capable of functioning effectively in such conditions. Additionally, the Kuiper Belt is home to countless small, icy bodies that are largely uncharted, increasing the risk of unexpected hazards. The difficulty in predicting the precise characteristics of these distant worlds adds another layer of complexity to mission design and execution. Yet the potential scientific rewards are nothing short of transformative. Pluto and its Kuiper Belt neighbors are relics from the early solar system, preserving pristine records of its formation and evolution. Studying these distant worlds can provide invaluable insights into the processes that shaped our planetary system billions of years ago. Pluto, with its dynamic atmosphere, ice-covered mountains, and possible subsurface ocean, has already shattered expectations about what a dwarf planet could be. Meanwhile, the Kuiper Belt as a whole holds clues to the building blocks of planets and the distribution of organic compounds, which could shed light on the origins of life itself. For scientists, the pursuit of knowledge about Pluto and the Kuiper Belt isn't just about understanding these icy bodies in isolation. It's about piecing together a broader narrative of cosmic evolution. So, what's next in the quest to uncover the unknown? Stay tuned, because Pluto's story is only the beginning. Pluto, once dismissed as a frozen wasteland on the edge of our solar system, is turning out to be a cosmic enigma that challenges everything we thought we knew. But what exactly has the James Webb Space Telescope uncovered about this mysterious dwarf planet? Today, we dive into the groundbreaking discoveries made by the James Webb Space Telescope about Pluto, a world that might not be as cold and lifeless as we once believed. From hidden oceans to potential signs of life, Pluto's story has just taken an astonishing turn. For decades, Pluto has fascinated scientists and the public alike. Once the 9th planet of our solar system, it was demoted to a dwarf planet in 2006. But despite its status change, it remains a subject of intense interest. NASA's New Horizons spacecraft, which flew by Pluto in 2015, unveiled its icy terrain and hinted at more secrets beneath the surface. Now the James Webb Space Telescope has taken that exploration to a whole new level. Using its powerful infrared capabilities, James Webb has pierced through Pluto's frozen atmosphere to reveal astonishing details. One of its most groundbreaking discoveries: Pluto may harbor a subsurface ocean beneath its icy crust. This finding reshapes our understanding of where life could potentially exist in the universe. Liquid water, one of the key ingredients for life, might be hiding deep beneath Pluto's surface, kept warm by heat generated in its core. But that's not all. Webb has detected evidence of cryovolcanism, volcanoes that erupt with ice instead of lava. These icy eruptions suggest that Pluto is far from geologically dead. Instead, it appears to be a dynamic world, with forces shaping its surface even now. The surprises extend to Pluto's atmosphere. Unlike the thin, static atmosphere once imagined, Webb's observations reveal a highly dynamic system. As Pluto orbits the Sun in its elongated path, its atmosphere sublimates, vaporizing when closer to the Sun and freezing back onto the surface when farther away. Webb has even detected unexpected organic compounds in the atmosphere. Could these complex molecules be hints of chemical processes akin to those that led to life on Earth? Even Pluto's largest moon, Charon, is proving to be more fascinating than we thought. Webb's data shows signs of tectonic activity on Charon, with massive cracks and canyons suggesting possible subsurface heating. This raises the tantalizing question: could Charon, too, harbor an underground ocean? Pluto's smaller moons present a fascinating puzzle that astronomers are only beginning to unravel. Unlike the more predictable orbits of larger moons around their host planets, these smaller moons, Nix, Hydra, Kerberos, and Styx, exhibit chaotic and irregular paths, almost as if they are tumbling through space. Their unpredictable orbits have baffled scientists for years and raise profound questions about the forces at play in this distant region of our solar system. These irregular motions point to complex gravitational interactions, not only between Pluto and its largest moon, Charon, but also among the smaller moons themselves. By studying these interactions, scientists hope to gain a deeper understanding of the dynamics of planetary systems and uncover secrets about the early solar system's chaotic and formative years. Pluto and its moons are thought to be remnants of the Kuiper Belt, a vast region of icy bodies left over from the formation of the solar system. The Kuiper Belt is often described as a frozen relic, a time capsule that preserves the conditions and materials from the early days of our cosmic neighborhood. Within this context, the study of Pluto's moons takes on greater significance. These small moons, with their strange orbits, could serve as keys to unlocking the mysteries of how the solar system came to be. Scientists theorize that the chaotic orbits of Pluto's moons are a result of past events, such as collisions, gravitational disruptions, or even interactions with other Kuiper Belt objects. Understanding these events could provide insights into the violent processes that shape not only Pluto and its moons, but also the larger structure of the solar system. One of the most intriguing aspects of Pluto's smaller moons is how they challenge traditional assumptions about celestial mechanics. For instance, Nix and Hydra are locked in what scientists call a spin chaos, meaning their rotations are highly irregular and unpredictable. This chaos is believed to be caused by the gravitational influence of Pluto and Charon, which exert a kind of tug-of-war on the smaller moons. The resulting instability makes it nearly impossible to predict the exact orientation of these moons at any given time. By studying this behavior, astronomers can better understand how gravitational forces interact in multibody systems, a topic that has implications for studying exoplanetary systems and other celestial phenomena. Moreover, the composition and surface features of these moons offer additional clues about their origins. Observations suggest that the smaller moons are made of water ice and other frozen materials, similar to what is found on Pluto and Charon. This compositional similarity supports the idea that Pluto and its moons share a common origin, likely forming from a massive collision that occurred billions of years ago. Such an event could have ejected debris into space, which later coalesced into the moons we see today. This theory aligns with the giant impact hypothesis, a model that has also been used to explain the formation of Earth's moon. If confirmed, the study of Pluto's moons could provide a broader framework for understanding how moons form in planetary systems across the universe. The irregularities in the orbits of Pluto's smaller moons are not just scientific curiosities. They also serve as natural experiments for testing theories about the dynamics of planetary systems. By analyzing how these moons interact with each other and with Pluto and Charon, scientists can refine their models of orbital mechanics. These insights are not limited to our solar system, but can also be applied to the study of exoplanets and their moons, particularly in systems where gravitational interactions are similarly complex. Pluto is no longer just a forgotten icy rock at the edge of the solar system. Thanks to the James Webb Space Telescope, it's now a dynamic, complex world that may hold clues to life beyond Earth. These discoveries challenge our understanding of habitability and open the door to exploring other icy bodies in the cosmos. Who knows what other secrets await? If you enjoyed this deep dive into the mysteries of Pluto, be sure to like, subscribe, and hit the bell icon for more cosmic explorations from our channel. Until next time, keep your eyes on the stars, because the universe is full of surprises.